All right, hello everybody. Today we are going to be talking about induced current. So here I have just an example pulled up, very similar to some of the stuff that we're going to be going over in class. So to start out, I just want to point out that we have a bar magnet with a north and south pole and just a loop of current, or sorry, a loop of wire. And so what we're going to be doing is walking through this table just to see the steps that we have to go through to figure out which direction our induced current is going. So to start out, we have to figure out which direction our B field is going in. And so with any bar magnet, we are going to have a B field that goes in towards the South Pole, through towards the North Pole, and it's going to come out and kind of go out and around. And remember that the B field is smaller the farther away from the source you are. And so these arrows relatively represent magnitude. And it'll come back around and it does the same thing on the other side. And this is very similar to the way that our Earth works with the magnetic north and south poles that we have. So if you ever Google B field around the Earth, this is something very similar to what you're going to see. And so from the observation point of our loop of wire, the B field is going to be pointing in the negative X direction. And so I'm going to take out all these other arrows and just leave the relevant one. And so I'll mark the B field in blue. And so the B field is going to be pointing in this left direction. So I will say to the left. And then our dA, this is something that you get to choose when you're solving these problems. It doesn't matter which direction the dA is, as long as it's perpendicular or normal to the surface of the cross-sectional area of your loop of wire. So we have this circle, and sometimes I like to take like a lid or a cap or something that I have to use as an example. So we have this circle shaped with a cross-sectional area, and we get to choose which direction our dA is going to be. And so if I'm looking at this, at the picture, and I see maybe I'll choose it to be going to the left. And so I'm going to take the circle, and my hand is going to represent dA. And so like I said, it should always be normal or perpendicular to the surface. And so I'm going to choose it to be going to the left. And so if I were to draw that here on the picture, I'll draw the dA in red. It's going to go this way. And again, this is normal, so that's 90 degrees. And when I fill it in, it'll be pointing to the left. And so in the notes, we talk about flux, right? And so we have a couple of characteristics of flux, one being the size, big or small, relative, and the sign, if it's negative or positive. And so what we determine initial and final is kind of like a before and after scenario of when the object is moved, because you have to have some kind of movement in order to induce a current. And so here I have on the left, I have this V, and that's indicating velocity and direction. And so we have our bar magnet moving in this case, not our wire. Our bar magnet is going to be moving to the left. And so in our initial position, it starts out at, this X distance. It starts out close and then it moves to the left. And so after it moves, if you kind of think mentally, it's going to move farther away from the wire. And so the wire is going to be farther away from the source of the B field. And so we know that from previous conversations that when you are farther away from the source, the B field is smaller. And so our flux, if we talk about the initial flux, it's closer. So that means that it's going to be larger. And like I said, this is all relative. And so we're going to say the flux initially due to the B field is big. And then as it moves farther away, as it moves to the left, as the bar magnet moves farther away from the wire, it's going to be smaller, right? And so then when we talk about sign, because we have positive and negative, we're going to be looking at the relationship between B and DA as vectors. And so if the B and DA are pointing in the same direction and they're parallel, that means that the flux will be positive. If they are pointing parallel but the opposite direction of each other, so this is called anti-parallel. So for example, if the B field was pointing to the right and the DA was pointing to the left, they're still parallel, but they're pointing in opposite directions. This is called anti-parallel. Then they would be negative. Then this would be a negative sign. But because they're both in the same direction, they're working with each other, so they're going to be positive. So this is a big positive number. And then our final flux, after it's moved away, nothing changes with the relationship between DA and B. The bar magnet isn't moving in any other orientation other than just straight and linear. And so nothing changes, it'll still be positive. And so we have a big positive and a small positive. Now, if you want, you can assign kind of like fake numbers to these values if it helps you when you determine the change in flux. So that's what the d flux dt is. And so this is the change. And when we talk about change or delta, we're doing final minus initial. So if I have a small number, say for example, we just put in a dummy number like small 2. So that's a positive number, it's pretty small. And a big number, say we say 10. So this is a big positive and small positive. If we do 2 minus 10, that is a negative number that we will get from that subtraction. And so we will be getting a negative change in flux. Now, we know from our notes that minus V induced is equal to d flux over dt. So V induced is the opposite sign of d flux dt. So this is going to be then a positive because negative V is equal to d flux dt, right? That's an equation that we have. And so it's always going to be the opposite of our d flux dt, our change in flux. And so now we have all these signs. So now what do we do to calculate I induced? So this V induced value, this signage, is going to tell you which direction to point your hand when you do the right hand rule. And so if we go back to the DA, we initially chose our DA to be in the left direction, right? Perpendicular to the surface or to the cross-sectional area. We chose it to be in the left direction. And our V induced is positive, so that means that we stay. Positive is good, stay. If this value of V induced, if it turned out to be a negative instead of a positive, that would mean that we would have to flip whatever we chose. And so we would go in the opposite direction. So in this case, if it were negative, instead of staying negative, bad, flip. So then we would flip and then we would do our right hand rule. In this case, we're good. We have a positive V induced. That means that we stay in the direction that we initially chose. So we chose to the left. Now, because when we do our right hand rule, we're talking about the way that the current is going through the wire. We could say clockwise or counterclockwise, but it's all a matter of perspective. And so usually we'll say into the page and out of the page around the loop. And so if I say, if my thumb is going to my left, then as I curl, I'm going into the page at the top and out of the page at the bottom. And so I usually will write this as, I'll redraw the circle. And as I go, as my fingers curl at the top of the circle, it's going to go into the page. And as it curls down, as my fingers curl, they're going to come out of the page at the bottom. And so we write that like this. Now, again, like I said, you can say counterclockwise or clockwise, but depending on which side of the circle that you're looking at, it can be described either way. So that can kind of be a little confusing. And so it's best if you have this representation and you talk about going into and out of the page, because that will always be the same regardless of what side you're on. Okay, so that's the example of how to figure out I induced from this table.